In this lesson, we learn exactly how to compute wide heteroskedasticity-robust standard errors for any regression model. This method is essential whenever the variance of the errors is not constant, that is, when your model suffers from heteroskedasticity. First, let's generate the necessary data. For our independent variable, x, we draw 200 random real numbers, uniformly distributed from 1 to 10. To generate the dependent variable, y, we begin with a simple regression model. Here, the model is shown in its general form with beta coefficients. Beta 0 and beta 1 are the intercept and slope coefficients. U is the error term. This is the same model in its specific form, where the coefficients are 2 and 1.5. In real-life applications, these true population coefficients are unknown. We estimate them using the classical method called ordinary least squares, or OLS. Next, we create a heteroskedastic error term, where the variance depends on x. The heteroskedastic error, or epsilon hetero, is a product of the independent variable x and random noise drawn from a normal distribution. By setting beta 0 to 2 and beta 1 to 1.5, and using the heteroskedastic error term, we generate 200 observations of the dependent variable y hetero. Here is the scatter plot of y hetero versus x. Because the error variance increases with x, the outcomes become more spread out. As we move toward the right, the observations widen, producing the classic fan pattern.
This is the matrix formula for estimating the OLS regression coefficients, the beta vector. It is derived using calculus. The X matrix contains 2 columns and 200 rows. The first column is a vector of ones, capturing the intercept. The second column contains the values of x, used to estimate the slope. In Mathematica, the beta vector is computed as the inverse of x prime x, multiplied by x prime, and then multiplied by the y vector, or y hetero. Using this data, we obtain the OLS estimates of the regression coefficients. Ordinary least squares gives coefficient estimates that remain unbiased under heteroskedasticity. But their standard errors become unreliable, which distorts t-tests and confidence intervals. Next, we compute the ingredients required to obtain the OLS standard errors for our estimated coefficients. Residual sum of squares is the dot product of the residual vector with itself. Degrees of freedom equals the number of observations minus the number of estimated coefficients. The variance of the residuals, conventionally called sigma squared, equals residual sum of squares divided by degrees of freedom. This definition of error variance is valid only under the assumption of homoskedastic errors. Because our data is heteroskedastic, we will later replace this term with White's robust estimator. In many contexts, the inverse of x prime x is called the information matrix, or the inverse Fisher information matrix, because it measures how much information the sample provides about the parameters. Under OLS, the variance-covariance matrix of the regression coefficients equals sigma squared multiplied by the information matrix. Standard errors are the square roots of the diagonal elements of this variance-covariance matrix. and the t-statistic is simply each coefficient divided by its standard error. However, because of heteroskedasticity, these standard errors and resulting t-statistics are unreliable. Some observations receive too much weight, causing OLS to underestimate the true variability of the beta coefficients. Hypothesis tests become misleading.
To fix this, White proposed an estimator that adjusts the variance formula to reflect the unequal error variances. The formula looks intimidating, so econometric Ians invented a mnemonic device called the Sandwich Estimator. The two outer matrices are the bread, and the middle matrix is the meat. Here is a more intuitive pictorial representation. The outer matrices, x prime x inverse, are the bread. In the center is the meat. The diagonal matrix plays a crucial role, because it replaces the single constant variance with appropriate weights for every observation. Let's visualize this in Mathematica for our numerical example. Here we define and generate the diagonal matrix. It is a 200 by 200 matrix, because our regression uses 200 observations. If we scroll the screen, we see that its diagonal contains the squared residuals, and zeros elsewhere. This is the so-called meat matrix, which is a 2 by 2 matrix in our simple regression example. And here we have the final white heteroskedasticity-robust variance-covariance matrix, produced by the Sandwich Estimator. From this, we obtain the robust standard errors and the robust t-statistics for our regression coefficients. Finally, let's compare the results. Notice that the standard error of the slope coefficient is larger under White's robust estimator than under OLS. As a result, the robust t-statistic is smaller, giving us a more accurate and reliable hypothesis test.